The following presentation was produced by the Clemson University Cooperative Extension Service through funding by the Southern Regional Aquaculture Center, United States Department of Agriculture, and the U.S. Fish and Wildlife Service, United States Department of the Interior.
As mentioned throughout this video series, successful fish production is dependent on the quality of water present. Tapes 1 and 2 of this series have introduced important water quality parameters and their influence on the biology and chemistry of a typical fish pond. However, in order to properly manage the water quality of a pond, methods of measurements of the various parameters must be understood. Therefore, the purpose of this tape is to describe the testing procedures and the water quality parameters which were discussed in tapes 2. Corrective measures for each parameter, if found to be at levels adverse to good fish production, will also be discussed. Testing procedures and corrective measures concerning total alkalinity and hardness were presented in tape 1 of this series. Throughout this video, water testing equipment such as kits and meters will be shown. Testing examples will employ a specific kit or meter simply for convenience. The producer of this video series did not endorse any of the particular kits or meters. Keep in mind that other kits and meters are available and procedures may differ slightly from the examples shown in this video. There are several methods to measure the abundance of phytoplankton. Economically speaking, the practical choice for most pond owners is the use of a Secchi disc. The Secchi disc is a circular object roughly 20 centimeters in diameter, constructed of metal or plastic, which is divided by black and white quadrants. It is suspended by a rod or a rope, which is marked in gradations of inches or centimeters. A weight is usually present at the bottom of the disc to ensure its sinkage. Secchi discs may be purchased from scientific supply houses, or they can be easily made. The principle behind the Secchi disc is that it correlates with the turbidity in pond water, and since turbidity in most fish ponds is due to phytoplankton, the Secchi disc is a good indicator of phytoplankton abundance. However, in some ponds, turbidity may be due to suspended clay. If this situation exists, the clay must be removed to ensure phytoplankton growth. Consult your county extension agent or aquaculture specialist if this problem exists. To obtain the Secchi disc visibility reading, the disc is lowered into the water until it just disappears and the depth is recorded. The disc is then lowered a little deeper and then raised until it just reappears. The depth at the reappearance of the disc is also recorded. The average of the two readings is the Secchi disc visibility. Conditions for obtaining the Secchi disc visibility should be standardized. Measurements should be taken around noon or early afternoon on calm, sunny days. A Secchi disc visibility of 30 to 60 centimeters is generally adequate for good fish production and for shading underwater plants. In ponds in which fish are fed, it is virtually impossible to regulate phytoplankton abundance. Therefore, the Secchi disc visibility is only a simple indicator of abnormal conditions. Heavy blooms in which Secchi disc visibility may be below 30 centimeters are usually transient, but under certain conditions may be a chronic problem. Usually, overabundant phytoplankton should not be reduced by chemical treatments, since sudden reduction may cause problems with dissolved oxygen. However, in some cases, such as in ponds with dense blue-green algae blooms, chemical treatments may prove to be beneficial. Consult your county agent or aquaculture specialist if you have any questions about chemical control of phytoplankton or large aquatic weeds. Dissolved oxygen. There are two methods of dissolved oxygen determination: the use of chemical kits and polographic meters. The kit method is usually more practical for a small producer or pond owner, while the use of meters is usually preferred on larger commercial operations. Kits may be purchased from scientific supply companies or from fish farming supply houses. Included in the test kits are a high-range and low-range method for dissolved oxygen determination. Initial testing should start with the high-range method. To measure dissolved oxygen using the water quality test kit, Proceed as follows for the high-range test. Obtain a water sample from the pond by using the glass stopper dissolved oxygen bottle provided with the kit. The bottle should be cleaned before and after each use. To clean the sample bottle, use dishwashing detergent, making sure that it is rinsed well with clean water, preferably distilled or tap water. The sample should be taken away from the pond bank to avoid vegetation. Sample away from aerators and inflowing water, and preferably with the wind at your back. This will usually give you the lowest reading in the pond. To take the sample, submerge the bottle approximately 1 foot below the surface. Unstopper to collect the sample, and then restopper the bottle under the water to ensure that no air bubbles are trapped. It is important that no air bubbles are present, since they will increase the dissolved oxygen value by dispersing the oxygen from the trapped bubbles into the water sample. Carefully remove the stopper from the bottle. Add the contents of 1 dissolved oxygen 1 reagent powder pillow and 1 dissolved oxygen 2 reagent powder pillow to the bottle. Stopper the bottle firmly to avoid trapping air. If the air bubbles are present, discard and obtain a new sample. Shake the bottle vigorously for a few seconds to mix. A flock will form, which will be brownish-orange if oxygen is present. Allow the sample to stand undisturbed until the flock has settled to the lower half of the bottle. Then shake the bottle again and allow the flock to resettle a second time below the line on the bottle. Remove the stopper and add 1 dissolved oxygen 3 reagent powder pillow. Restopper and shake several seconds to mix. If air bubbles result, obtain a new sample and start over. After shaking, the flock will dissolve and a yellow color will develop if oxygen is present. This is now referred to as a prepared sample. Rinse the plastic measuring tube with the sample, then fill and pour the contents into the mixing bottle. Add PaO standard solution drop by drop to the contents of the mixing bottle. Swirl the mixture after adding each drop while dispensing the drops with the dropper directly above and vertical to the mixing bottle. Add until the color changes from yellow to colorless. Be sure to count the number of drops while adding them. The number of drops required to change the sample from yellow to colorless is equal to the dissolved oxygen concentration in milligrams per liter. For example, if it took 7 drops for the color to change, then the sample contains 7 milligrams per liter or parts per million of dissolved oxygen. If the results obtained in the high-range test are below 3 milligrams per liter or parts per million, proceed with the low-range test. In the low-range test, a larger prepared sample is used, which results in a greater sensitivity at low dissolved oxygen concentrations. To measure the dissolved oxygen using the low-range test, proceed as follows. Using the prepared sample remaining from the high-range test in the stopper dissolved oxygen bottle, pour off the excess until the level is at the 30 ml mark on the bottle. Add PaO solution drop by drop until the color changes from yellow to colorless. As in the high-range test, record the number of drops used. In the high-range test, each drop of PaO solution equals 1 milligram per liter of dissolved oxygen. In the low-range test, 5 times the amount of sample was used than in the high-range test. Therefore, each drop is divided by 5 and equal to 1/5 of a milligram per liter of dissolved oxygen. In other words, each drop of PaO equals 0.2 milligrams per liter dissolved oxygen. Recall that 0.2 is equal to 1/5. So if, for example, 6 drops were added in the low-range test, the dissolved oxygen would be 6 multiplied by 0.2, which equals 1.2 milligrams per liter dissolved oxygen. Note that the same result is obtained if 6 is divided by 5. There are generally 2 types of oxygen meters which are commonly used on commercial fish farms. These are temperature compensating and non-temperature compensating meters. They are both operated in basically the same manner, but with some differences which will be pointed out in our discussion. To take the dissolved oxygen reading using a meter, proceed as follows. First, switch the meter to the off position and, if necessary, adjust the needle to read 0 by rotating the screw below the scale. If your meter has a red line knob, switch it to this position and adjust the knob so that the needle is directly over the red line. If this adjustment is not possible, it is a good sign that the meter's batteries are failing and should be recharged or replaced. A 15-minute warm-up period is required by most oxygen meters to polarize the probe. The probe should be wrapped in a wet cloth or paper towel during the calibration procedure. Switch the meter to the 0 position and adjust the knob so that the needle is at the 0 position on the scale. If your meter has a full scale knob, switch it to this position and adjust so that the needle reads 15 milligrams per liter on the scale. This adjustment is similar to the red line adjustment of the other type meter and is a check for battery strength. Therefore, a full-scale reading cannot be obtained. The batteries need to be recharged or replaced. At this point, the operation of each meter will be discussed separately. If your meter has a calibration scale located above the oxygen and temperature scales, switch the meter to the calibration position and adjust the knob so that the needle indicates the local altitude in feet. Allow time for the needle to drift, then readjust until a stable reading is obtained. Once the calibration reading or the altitude reading is stable, switch the meter to the temperature position. The temperature of the pond water is then taken by placing the probe in the water and moving it back and forth. It is desirable to take the temperature reading where the oxygen reading will be taken. Be sure the reading is taken away from the pond bank, incoming water, aerators, and if possible with the wind at your back. Submerge the probe about 1 foot below the surface. The probe may be attached to a rod or pole with tape, which will allow it to be extended into the pond and reduce the cable stress. Once a stable temperature reading is obtained, rotate the large dial on the meter to the correct temperature. Note that the temperature dial has a white line which takes into account the salinity of the pond. For example, if your pond is 1/2 the salinity of seawater and the temperature of the water is 20 degrees C, the dial is rotated so that the 20 degrees C line meets the middle of the white line. The meter is then switched to the read O2 position and the probe is placed back into the water. The probe is then moved back and forth until a stable reading is obtained on the scale. If your meter does not have an altitude scale, it is most likely a temperature compensating meter. It must be calibrated in a different manner. First, switch the meter to the temperature position and read the air temperature. Determine the calibration value for this temperature from the table on the back of the meter. For example, if the temperature is 21 degrees C and the altitude is 1,000 feet, the calibration value from the Table 1 on the back is 8.9 milligrams per liter. From Table 2, the altitude factor is 0.96. This value is a correction factor and is multiplied by the calibration value from Table 1 to get the correct calibration value. Therefore, in our example, 8.9 milligrams per liter times 0.96 is equal to 8.54 milligrams per liter. Switch the meter to the 0 to 10 or 0 to 20 milligram per liter range and adjust the meter with the calibration knob until the derived calibration value is obtained on the appropriate scale. For example, to enter a calibration value of 8.54 using the 0 to 20 milligram per liter range, the meter is switched to this position and then adjusted to 8.54 milligrams per liter. Be sure to allow time for the needle to drift and readjust if necessary. The meter is now ready to take a reading. Remember to take the reading away from the pond bank, aerators, incoming water, algal blooms, and if possible, with the wind at your back. Submerge the probe about 1 foot below the surface. To get an average value of dissolved oxygen for your pond, it is a good idea to sample at several different locations, whether you use a kit or a meter. If the oxygen reading is made near incoming well water, as shown here, the value will be low since well water is low in oxygen. On the other hand, if oxygen is measured in dense algae bloom, the reading will be abnormally high during the day and abnormally low at night. Oxygen will also be higher near aeration devices. It is also unwise to simply throw the probe out into the pond, since the probe and cable may be damaged and the probe will sink into the mud. If properly used and cared for, your oxygen meter may be used for many years with little maintenance. Besides changing and recharging the batteries, the only part of the instrument that requires periodic care is the probe. The oxygen probe is covered by a thin membrane which should be replaced every 2 months or so, or when air bubbles are present below the membrane. To change the membrane, proceed as follows. Prepare the potassium chloride probe solution by dissolving the crystals in distilled water. Unscrew the protective cap and remove the O-ring and the old membrane. Rinse the exposed sensor thoroughly with the probe solution. Grasp the probe in your left hand and fill the sensor body with the probe solution while pumping the diaphragm button with a pencil. Continue to fill and pump until no air bubbles are present. Place a new membrane over the sensor, and while holding one end with your left thumb, pull the other end up and over the sensor. Stretch the membrane slightly as you pull it over the sensor. This usually requires some practice before you can put the membrane on without leaving any air bubbles. If no air bubbles are present, replace the O-ring and trim off the excess membrane. Replace the protective cap. Periodically, the probe's metal electrodes have to be reconditioned. Reconditioning kits are available from the manufacturer, and the procedure is rather simple, as you can see. One problem that commonly occurs is needle jumping, which is usually a result of a short in the cable. To help prevent this, tape the probe and cable to a pole. During the summer, dissolved oxygen should be recorded twice daily, ideally at dawn and dusk. Records should be kept which may indicate trends which may affect fish if corrective measures are not taken. During the cooler months, where there is less danger of oxygen-related fish kills, measurements may be reduced or discontinued, depending on the stocking density of the pond. A simple model may be constructed from oxygen measurements taken during the evening and night, which when used properly can accurately predict the oxygen concentration of the pond at its lowest level. And since this low usually occurs near dawn, it also may save the producer some sleep. An example of predicting the low oxygen concentration is shown in the two graphs. In Pond A, the dissolved oxygen was measured at 8 p.m. and again at midnight, and the values were plotted and a straight line was drawn to connect them. From the value observed at midnight, the line was extended to dawn. In this case, the extended line is dotted. In this example, Pond A should have adequate oxygen at dawn, while Pond B probably will not. However, the predictive models are not always foolproof. Therefore, they should be used with caution. For example, if after using the model your pond resembles the situation in Pond A, it may be wise to measure the concentration at dawn periodically to be safe. If oxygen levels decline low enough, corrective measures are warranted. The most common method to alleviate low oxygen concentration is aeration. There are a variety of aeration devices which differ in both cost and performance. Small pond owners often install electric floating aerators and simply run them continuously throughout the night. However, in production ponds, emergency aeration is usually the rule. A tractor-driven paddle wheel or pumps are commonly used. When possible, permanent electric paddle wheels with at least 1 horsepower per acre are recommended for catfish ponds. The principle behind all of these aeration devices is exposing small bubbles of water to the air, thereby increasing the surface area for diffusion. As water is splashed, more of it is allowed to contact the air, thus promoting diffusion of oxygen into the water. Another type of aeration is accomplished by devices which move air or oxygen into the water, such as air blowers. These are usually not practical in pond culture, but are commonly used in holding tanks and hauling containers. Pumping water into the pond seldom helps raise oxygen levels unless the water is pumped over a splash device or sprayed out over the pond, thereby allowing oxygen to diffuse into the well water. This is because most well water is nearly devoid of dissolved oxygen. If possible, it is best to utilize aeration devices. As mentioned, there are many models to choose from. Consult your county agent or aquaculture specialist for assistance in making your decision. There is also information available on oxygen transfer coefficients for various types of aerators in most state extension offices. Carbon dioxide. Carbon dioxide may also be determined by the kit method. However, a more convenient method is available which is highly accurate. By measuring the pH, temperature, and total alkalinity of the water sample, the carbon dioxide concentration in milligrams per liter may be determined by this table. For example, if the pH is found to be 7, the temperature 20 degrees C, the corresponding factor from Table 1 is 0.211. This factor is then multiplied by the total alkalinity of the sample, resulting in the carbon dioxide concentration in milligrams per liter. As an example, let us say that the total alkalinity of the sample was determined to be 75 milligrams per liter as calcium carbonate. Therefore, 75 times 0.211 is equal to 15.83 milligrams per liter of carbon dioxide. Note, as the pH decreases, the factor gets larger, which shows that more carbon dioxide is present in acidic waters of similar alkalinities. The table shown here is condensed for convenience. However, tables showing factors for a wide range of pH and temperatures may be obtained from your county agent or aquaculture specialist. If carbon dioxide levels are elevated, it is usually due to inadequate aeration of groundwater or following a phytoplankton die-off. Aeration of the water usually helps remove the carbon dioxide. As mentioned in Tape 1 of this series, adequate dissolved oxygen helps prevent carbon dioxide toxicity. Therefore, if dissolved oxygen levels are maintained, there is usually not a problem with carbon dioxide. pH. There are two methods to measure pH, by kit and by meter. As with dissolved oxygen determination, the kit method is less expensive and therefore more practical for pond owners. To test the pH using the test kit method, proceed as follows. Obtain a water sample away from the pond bank in a clean jar or bottle. Rinse the 2 color viewing tubes with the sample water. Fill each to the 5 ml mark. Add 6 drops of wide-range pH indicator to one of the tubes and swirl to mix. Insert the tube into the opening on the right side of the color comparator. Insert the other tube into the left opening. This tube is the untreated sample and simply cancels out any color resulting from the pond water. Hold the comparator up to the light source and rotate the disc until the color on the wheel matches the color in the sample. Read the pH through the scale on the window. pH may also be measured using a narrow range method. The smaller range allows for more accuracy. There are several narrow range kits available, but the most common is Thymal Blue Test, which measures pH values between 7.8 and 10, which are the most common pHs in pond water. Narrow-range test kits are not included in most large kits and must be purchased separately. It is important to remember to first check your pH using the wide-range method and then, if greater accuracy is desired, use the narrow range test. To test the pH using the narrow range method, proceed as follows. Obtain a water sample as described for the wide range test. Fill the 2 viewing tubes to the 5 ml mark with the sample. Add 6 drops of the thymal blue indicator solution to one of the tubes and swirl to mix. Insert this tube into the opening on the right side of the color comparator. Insert the other tube into the left opening. Hold the comparator up to the light source and rotate the disc to obtain a color match. Read the pH from the wheel. The pH may also be measured with a meter, but most meters are expensive. However, a less expensive version of a typical pH meter is available. An example of this is commonly called a pH pin. To use this instrument, proceed as follows. Remove the plastic boot from the meter. Check the calibration of the meter by immersing the probe into a buffer of a known pH. The buffer should be within the normal pH range of the pond. Buffers may be purchased from scientific supply companies. To calibrate, adjust the calibration screw until the instrument reads the value of the buffer. Calibration should be done periodically, such as once every few days. To measure the pH, immerse the probe into the water to be sampled. Do not exceed the warning line shown on the meter. Stir back and forth and observe the reading. This particular model has a hold button which will lock the reading on the display after the probe is withdrawn from the sample. After each use, rinse the probe with clean water, preferably distilled if available. Since pH, like dissolved oxygen, fluctuates diurnally, readings should be taken at dawn and at dusk to get an idea of the total variation in pH. pH should be checked regularly, but measurements usually don't have to be as frequent as those for dissolved oxygen. If through measurements a pH problem is determined to exist, corrective measures should be taken. Normally, pH problems are related to the magnitude of fluctuation of pH from morning to evening. This may be solved by the addition of buffering agents such as lime. Since pH is a function of alkalinity and hardness, corrective measures involve these 2 parameters and are discussed in detail in Tape 1 of this series. Nitrogen. As discussed in Tape 2 of this series, there are 2 nitrogenous compounds which often cause problems in fish culture. These are ammonia and nitrite. Ammonia. Ammonia may be determined easily by using a test kit method. To measure ammonia using the test kit method, proceed as follows. Obtain a water sample in a clean jar or bottle away from the pond bank. Remember, it is very important that a jar or bottle be clean. Rinse and fill the 2 color viewing tubes to the 5 ml mark. Add 1 drop of Rochelle salt solution to one of the tubes if the total hardness is above 100 milligrams per liter as calcium carbonate. Add 3 drops of Nessler's reagent to the same tube that the Rochelle salt solution was added. Swirl to mix for several seconds. Allow 10 minutes for the color development. If ammonia is present, a yellow color will be evident. Insert the tube, which contains Nessler's reagent, into the opening on the right side of the color comparator. Insert the other tube containing untreated sample into the left opening. This tube cancels out any color resulting from the pond. Hold the comparator up to the light source and rotate the disc to obtain a color match. Read the disc to obtain the milligrams per liter total ammonia nitrogen. To convert this value to milligrams per liter of total ammonia, multiply by 1.2. For example, if the wheel reads 1.5 milligrams per liter ammonia nitrogen, the total ammonia is 1.5 times 1.2, which equals 1.8 milligrams per liter total ammonia. Most fish culturists refer to total ammonia concentration, hence this conversion is usually performed. If the reading on the wheel is greater than 2.8, or 90% of the maximum, it is necessary to perform a dilution of the sample so that the reading is within the color range which will be detected by the color comparator. A 5-fold dilution generally solves this problem. To do a 5-fold dilution, fill a calibrated eyedropper provided to the 1 ml mark with pond water. Transfer this into one of the tubes and repeat for the other tube. Then add 4 ml of distilled water to each tube. This makes a total of 5 ml of diluted sample, and this sample is diluted 5-fold. Then, test for ammonia as described. The results read off the color wheel is then recorded. This value must be multiplied by 5 to convert it to the true undiluted value. For example, if the wheel reads 0.8, the true value is 0.8 times 5, which equals 4 milligrams per liter ammonia nitrogen. Again, to convert this to total ammonia, multiply by 1.2. In our example, 4 times 1.2 equals 4.8 milligrams per liter total ammonia. The toxic form of ammonia, or the unionized, should be calculated using temperature and pH. This procedure involves using a chart as described in tape 2 of this series. It is generally sufficient to sample a pond for ammonia once every 2 weeks. This schedule should be maintained throughout the year. Sampling frequency may be increased during the late summer and fall, since this is usually the high ammonia season. If elevated ammonia levels are present in the pond, there are only a few corrective measures that can be taken. One option, although expensive, is to pump water into the pond, thereby flushing out the ammonia. Preventative measures are much more effective in controlling ammonia. These include limiting the stocking density of the pond, correcting elevated pH if present, and not exceeding a prescribed feeding rate. Nitrite. Although nitrite is less of a problem in pond culture, levels may increase to lethal ranges in a relatively short period of time. Therefore, ponds should be checked for nitrite at least twice weekly, primarily in the fall through the spring months. To measure nitrites using the kit method, proceed as follows. Collect a water sample in a clean jar or bottle away from the pond bank. Remember, always use a clean container for sampling. Rinse the color viewing tube several times with the water sample. Fill the tubes to the 5 ml mark. Add 1 nitrite reagent powder pillow to the tube, then stopper and shake to mix for several seconds. A pink color will develop if nitrite is present. Allow the sample to stand for 10 minutes. Insert the tube into the opening on the right of the color comparator. Fill the other viewing tube with 5 ml of water from the sample and insert it into the left compartment. This tube cancels out any color that is present from the pond water. Hold the comparator up to a light source and rotate the disc to obtain a color match. Read the disc to obtain the milligrams per liter of nitrite nitrogen. To convert this value to milligrams per liter of nitrite, multiply the value on the disc by 3.3. For example, if the value on the disc reads 0.35, then 0.35 times 3.3 equals 1.15 milligrams per liter nitrite. Most fish farmers convert to nitrite. If the reading on the wheel is greater than 0.45 or 90% of the maximum, a dilution of the sample is necessary so that the reading is within the color range which is detected by the color comparator. The same procedure which was used to dilute the sample when testing for ammonia is carried out so that the sample is diluted 5-fold. After the dilution is performed, test for nitrite as described above. Make sure to dilute before you add the nitrite powder pillow. If diluted, the value on the color wheel then must be multiplied by 5 to correct for the dilution. For example, if the disc reads 0.18, then 0.18 times 5 equals 0.9 milligrams per liter nitrite nitrogen. Again, to convert this to nitrite, multiply by 3.3, so 0.9 times 3.3 equals 2.97 milligrams per liter nitrite. Since nitrite levels are related to the ammonia levels, corrective and preventative measures for ammonia apply to nitrite as well, with one exception. Since the toxicity of nitrite depends largely on the amount of chlorides present, the addition of chloride, usually in the form of sodium chloride or common table salt, may prevent deaths due to nitrite toxicity. If nitrite levels are found to be 0.5 milligrams per liter or above, your water should be checked for chloride to see if enough is present to prevent nitrite toxicity. There are usually two procedures to test chlorides in water quality test kits: the high range and the low range test. The low range test is normally used in freshwater culture operations, and therefore it is this test that we will describe. Once the chloride concentration of the pond is known, it may be compared to the amount of chloride needed by using the following formula, where N is equal to the nitrite concentration and C is equal to the chloride concentration. Either 3 or 5 times the nitrite concentration minus the existing chloride concentration is equal to the number of parts per million chloride needed. 3 will generally keep the fish from being stressed, but since salt is cheap, 5 times the nitrite concentration is often used to help ensure protection. If the number derived is negative, no treatment is necessary. If positive, the number of parts per million chloride should be added to the pond water. To test water using the low-range chloride test, proceed as follows. Collect a water sample in a clean jar or bottle away from the pond bank. Fill the mixing bottle to the 23 ml mark as shown with this water sample. Add 1 chloride indicator powder pillow to the mixing bottle and swirl to mix. An orange color will develop initially, then a yellow color will be present. Add silver nitrate solution drop by drop to the mixing bottle while holding the dropper vertically above the mixing bottle. Swirl the sample after the addition of each drop. Be sure that the drops are counted as they are added. Add drops until the color changes from yellow to orange and remains so. The sodium chloride concentration in milligrams per liter is the number of drops times 12.5. For example, if 10 drops were required, then the concentration will be 10 times 12.5, or 125 milligrams per liter. To convert the results to milligrams per liter of chloride, multiply the milligrams per liter of sodium chloride by 0.6. In our example, the value of 125 times 0.6 is equal to 75 milligrams per liter chloride. This conversion is usually made since the chloride concentration must be known to prevent nitrite toxicity. In order to save time when testing water quality, a technique of multiple sampling may be used. For example, you can test all your ponds at once for both ammonia and nitrite if the correct number of tubes are set up. Addition of reagents then takes place as described previously. In summary, a major key to producing and maintaining healthy fish is proper management of water quality. By following the guidelines in this tape, you should be able to apply sound management which will result in better fishing for the farm pond owner and increased profits for the commercial fish farmer. For information on ordering supplies and other equipment and other information regarding water quality testing, consult your county agent or aquaculture specialist.